What we're going to talk about in this lesson is measures of spread. And anytime you talk about data, you need a measure of center, like we talked about in 3.1, and you need a measure of spread. And I want you to look at this first problem. It says, suppose you were deciding between living in San Francisco and St. Louis. One thing you might consider is weather. The table presents average monthly temperatures in degrees Fahrenheit for both cities. The mean temperatures of both cities are similar, 57.5 for San Francisco and 56.1 for St. Louis. So something you really wouldn't notice a difference in. However, temperatures in St. Louis are more spread out than those in San Francisco. The mean only gives a measure of center, but to describe a data set, we also need to measure the amount of spread. And I want you to look at the graph. Like San Francisco's mean would be roughly right there, and St. Louis would be roughly right there. But look at your dot plot and look at how close the temperatures are in San Francisco, and look at how spread the temperatures are in St. Louis. And that's what we're going to talk about today. The first thing we're going to talk about is a range. And the range is a measure of spread. It is the difference between the largest value in the data set and the smallest value. All right, so for example, if you look at San Francisco and you look for and these are average monthly temperatures, it definitely could be warmer than 63 on a day in September. But if you look in September, that's their highest monthly average temperature is 63, and the lowest is January for a spread of just 12 degrees. And if you look at St. Louis, their highest is July, 79, and their lowest is 30 for a spread of 49 degrees. St. Louis would be more like Salisbury, Maryland. San Francisco is very different. Now, I like the range because it's easy. You saw what we did. It's not often used in practice because the range only involves the two values in the data set. You all saw what I did, the highest, the largest value, and the smallest value. So we need to do something that brings in more of the data or all of the data. And what we're going to do with that is the variance. And when a data set has a small amount of spread, like San Francisco, most of the values are close to the mean. When a data has a larger amount of spread, more of the data values will be far from the mean. The variance is a measure of how far the values in a data set are from the mean on average. The variance is computed slightly differently for populations and samples, and we're going to start with population variance. And here's my data. The x1, x2, x3, ... x big N denote the values in a population of size big N. Remember, anytime you see big N, it means population. Let mu denote the population mean. The population variance denoted by, this symbol is called sigma squared, is, and I want you to write a couple of those symbols. Sigma squared, sigma squared. And here's what we do. We're going to take a sum like you did in Algebra 2. We're going to do x minus mu. We're going to square, and we're going to divide by n. Now, when you look at the formula, it looks like a lot. It is not that bad. It just takes a while to do. Where this symbol tells me I'm going to take a sum. X is my data. What are my temperatures in San Francisco or St. Louis or whatever my data is. Mu is my mean. And you're going to divide by big N, which is the total. And this is for population. And that's how we're going to find the variance. And I want you to go back and look at the graphs for a minute. I definitely cannot tell what the variance is by looking at the data. But here's what I know. If you look at San Francisco, it's going to have a much smaller variance than St. Louis because the data in San Francisco is much closer to the mean than St. Louis. So that's what I know. San Francisco is going to have a smaller variance than St. Louis. All right, and here's our problem. It says compute the population variance for the San Francisco temperatures. And what population variance is, and this is San Francisco, I'm going to do it in blue, it's sigma squared. All right, and here's what I know. I know mu was 57.5 for San Francisco. And I want you to look at your columns. The first column, they give you x. The second column, they give you x minus mu. What this is the actual minus the predicted. All right, and what they do in the next column is they square it. Okay, so actual minus predicted, and we square it. And remember we talked about the mean. Like if I asked you, what do you think the temperature is today in San Francisco, and you didn't have that table to look at, you would always guess the mean. You would say, I think it's 57.5. All right, what I want you all to do, and I'm going to do a couple of them, and then I want you to pause the video. I want you in this column to write down your actual minus predicted. All right, actual minus the mean. Data minus mean. Pause your video and write those down, please. All right, once you have them written, I want you to go to your calculator. And the first one, I'm going to do 51 minus 57.5 and hit enter. And I get negative 6.5. Now, what I want you to do is square that. And the square button is on the right side. It's at x squared. Hit x squared. And it's going to square to 42.25. All right, go to your next one, and I'm going to do 54 minus 57.5. Enter, and I get negative 3.5. And same thing, I'm going to square it, enter, and I get 12.25. 55 minus 57.5, enter, square it, enter, and I get 6.25. And I forgot to write this one here. It's going to be negative 2.5. 56 minus 57.5, enter. Negative 1.5. Squared, enter, 2.25. We're going to do one more together. Then I want you to pause the video and finish this list. I've got 58 minus 57.5, enter. 0.5 squared, I hit the wrong button, squared, enter, and my calculator didn't like that. 0.5 squared is 0.25. Pause the video and finish this table, please. Once you're finished, you've got your two columns. This first column is called deviations. It's how far the data deviated from what I expected. And what we've done in the second column is we've got square deviations. We squared everything. Now, if you add the columns, this middle column will sum to 0. That's why mathematicians said, let's square it so it doesn't turn to 0. And we square it in the second column. And if you pause the video and add them, and you'll come up with a sum of 169. Now, back to our formula. Here's our formula for variance. It's the sum of the quantity x minus mu squared divided by big N. And if you look at our table, we've already done that. We've done the sum. X minus mu squared, we got 169. And I'm going to divide it by 12 months in the year. So I'm going to do 169 divided by 12. And I'm going to do 14, I'm going to do 3 decimals, 14.083. So my variance is 14.083. And the bad thing about this variance is we squared the deviations. So the units of this are squared degrees. That doesn't make sense in the problem to talk about square degrees with temperature. So we will discuss that in a minute, what to do about it. Now, before we do that, I want to talk about sample variance. And when the data values come from a sample rather than a population, the variance is called the sample variance. The procedure for computing the sample variance is a little bit different. Some of it's obvious. You're going to use x bar in place of mu. The symbol is different. It's x squared. It's s squared. And here's the formula. I'm going to take a sum, and I'm going to do my actual minus my predicted, and I'm going to square it. The big difference is instead of dividing by n, you're going to divide by n minus 1, where little n is my sample size. And if you read over this, it tells you why we do that. But the gist of it is when you take a sample, you're trying to always estimate population, and using n minus 1 gives you a better estimate of the population. All right, so I want you to look at this data. A new type of battery is being tested for laptops. The lifetimes and hours of 6 batteries, and it gives them to you. And I want you to find the sample variance. So we're going to use our new formula. Now, I want you to list your X out in this column. In the second column, what we're going to do is, like what we did before, we're going to do our actual minus predicted, or our deviations. And in the third column, we're going to do just like we did before, we're going to do the squared deviations. So find the mean of that data, add it up and divide by 6, and you're going to come up with x bar equals 4. So I expect my battery to last 4 hours. So if you look at the first column, I'm going to do 3 minus 4, which is -1. It deviated. It lasted 1 hour less than I thought, -1. Square it, I'm going to get 1. The next one is 4 minus 4, 0. Squared is 0. 6 minus 4 lasted longer than I thought, 2 hours more. 2 squared is 4. 5 minus 4 is 1. 1 squared is 1. 4 minus 4 is 0. 0 squared is 0. And 2 minus 4 is -2. Squared is 4. Now, if you look at your data, you can look at the middle column and see that the 2's will cancel, the 1's will cancel. It sums to 0. If you look at the last column, 4, 8, 9, 10, it sums to 10. And the only way the last column could sum to 0 is if all of your data was the same as the mean. So all of your data was 4. All right, so here's what I got. Now going back to the formula, here is the formula for variance. It's the sum of the quantity x minus x bar squared divided by n minus 1. We've already done the work. It's 10 divided by n minus 1, so 6 minus 1. That's the part that you need to be careful of. So it's 10 divided by 5. The variance is 2. So my variance is 2. And the same as before, the bad thing about that is that it's in hours squared. And you know that doesn't make a whole lot of sense when you're talking about data to change the units. We'll fix that in a minute. When you look at this, I definitely cannot look at that and find the variance for St. Louis. It would take me a long time to do that by hand. I'm going to give you the variance for St. Louis, and I'm going to show you in a minute how to do it on the calculator. Here's the variance for St. Louis. Now, I don't know what it is, but I know it's got to be bigger than San Francisco because St. Louis is more spread. All right, so here's St. Louis. It's much bigger. It's 291.91. And here's what this means. It means St. Louis temperatures are more spread out. They're further from the mean than San Francisco. That's what that variance means. Now, I told you about the units being a problem. We're going to talk about standard deviation next, and you've probably heard of standard deviation. The variance is computed using square deviations. The units are not the same. They're squared. What we're going to do to find the sample standard deviation and the population standard deviation is just take the square root of the variance. So it's real easy. Once you've done the variance, your work is almost finished. I'm going to take the square root of the variance. And same thing here, the square root of the variance. And here's our population variance of San Francisco. I want the standard deviation. So what the standard deviation is going to be is just the square root of 14.083. On your calculator, the square root button's right beside x squared. And I'm going to type 14.083. And I'm going to get that. And I'm going to do 3 decimals. 3.753. And this would be degrees. Okay? And what that means is on average in San Francisco, the mean temperature is 57.5. However, it will vary by an average of around 4 degrees. That's how far the data is on average from the mean. The battery, I'm going to do the same thing. I'm going to take the square root of 2. And I'm going to get this. I'm going to get 1.414. And this is hours. All right, so I expect my battery to last 4 hours. However, this could vary by about 1.5 hours. That's what that means. It's how far the data is from the mean. What we're going to figure out here, recall that a statistic is resistant if its value is not affected much by extreme values, large or small. And I want to try to figure out if the standard deviation is resistant. And I want you to think about San Francisco. If we had had an extreme temperature, do you think it would have drastically affected the standard deviation? And that's what we're going to talk about today. But here's what I want you to do. I'm going to show you how to do this on the calculator. The first one, I want the sample variance, S squared. And I want the sample standard deviation, I want S. All right, so I want you to go to your calculator, hit the home button, and I'm going to go into statistics. And I'm going to go into that first column that's data. You see I'm already in there. And I'm going to enter that data into the calculator. Each time just push enter. All right, and once you're done with that, I want you to go back up to the top. We're not going to graph it yet. I want you to just go over to stats and hit enter. And what that does is give you all the stats for this data. There's stuff that we don't need yet. We'll talk about it later. But I want you to look. We talked about median before. There's the median. The mean, now this is the population mean. Remember, that doesn't matter. But we do not, you do population and sample the same. But we do not want this population standard deviation. That's incorrect, or variance. So go down to your sample mean, 2.5, same thing. The sample standard deviation is, I'm going to do 3 decimals, 1.927. That's standard deviation. And the sample variance is 3.714. I'm going to do 3 decimals on that too. I want you to go back up. And I want you to go to your data. And what I'm going to do is show you how to clear out your column. I'm going to sit on value, and I'm going to push EXE, and I'm going to clear it. All right, and it asks you to confirm because you might have messed up. And I want you to enter this data, 79, 20. All right, and here's what I want this time. I want the population variance. Remember, we divide by something different. And the population standard deviation. Okay, so I want sigma and sigma squared. So I'm going to go back in here. I'm going to go over to my stats. Gives me a lot of information. Go to where you see this mean that's population. That's where your population data is going to come in. My population standard deviation, I'm going to list that just like it is, the whole thing. 24.30821. And the variance, I'm going to do the same thing with variance. 590.38 and a 9. Okay, so that's what we've got with that. population variance and population standard deviation. Now, what I want you to do, I want you to go back into this data, and I want to change that 12 to a big number. So here's what I want you to do, and I'm showing you how to change a number too. I want you to go to that 12, and I want you to make it 1,000. Okay? And I want you to go to your stats. And I want to see what happened to that standard deviation. All right, so I'm going to go down to population, standard deviation, and look what it did. Okay? The standard deviation, it changed a lot. The standard deviation is changed a lot by extreme values. The standard deviation is not resistant. It's like the mean. The standard deviation and the mean cannot resist the pull of those large numbers. What we're going to talk about now is something called the empirical rule. And we've talked about bell-shaped histograms before. Many histograms have a single mode near the center of the data and are approximately symmetric. Such histograms are often referred to as bell-shaped. Notice how they've taken the histogram and they've approximated it by using that curve. And we're going to talk about the empirical rule. When a data set has a bell-shaped histogram, it's often possible to use a standard deviation to provide an approximate description of the data using a rule known as the empirical rule. And here's what the empirical rule tells us. It's a real important rule from statistics. When a population has a histogram that's approximately bell-shaped, then approximately 68% of the data will be one standard deviation from the mean. And if you look at this picture down here, this is what we're talking about. Approximately 95% of the data will be two standard deviations from the mean. And almost all of the data will be three standard deviations from the mean. And I want you to go back to the previous page. You've got a white space. I'm going to show you how to draw this normal curve. All right, so here's what I want you to do. I want you to draw a number line, and I'm going to put a mu in the middle, and I'm going to go 1, 2, 3. I'm going to go mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. And I'm going to do the same thing on the other side. I'm going to go 1, 2, 3, except I'm going to subtract. So I'm going to do mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. Now, the way I draw my curves, I go to mu and I put a point, okay, above mu. Go to your mu plus sigma, make a little tiny point about halfway, look at this distance, and about half of that distance. That's not the point you want. Go to the middle of the top half, the middle of this, and put a point. That's going to be the one that we're going to use. All right, once you do that, go to mu plus 2 sigma. Go to about where half of this distance is. Put a point. That's not the point we're going to use. We're going to do a point in the middle of this. The bottom half, I'm going to put a point. I'm going to erase that. Mu plus 3 sigma, you're going to put a point right on the axis. And on the other side, just match up your points. You don't want to try to measure it because it's not accurate enough. It will not match. And then your goal is to have a curve that looks like that. Okay, so then sketch in your curve. All right, and what that tells us, many of you have done areas under the curve from pre-calc or calc. What that tells us, if I go one standard deviation away from the mean, I'm picking up 68%, about 68% of the population. The area under the curve is 0.68. Okay, so I'm picking up 68%. If I go 2 standard deviations, I'm picking up 95%. And this is approximately every time. So the area under the curve is 0.95. And if I go 3, I'm picking up almost all, and your book right now uses 100%. Okay? Now, sometimes you can answer the question fine with this, but sometimes it's going to ask you more specific questions, so you need more detail. So what I like to do is I'm going to go into my curve, and I'm going to split the 68 in half. And I'm going to say, well, this is 34%, and this is 34%. Now, this and this, I'm going to do the same thing. And I'm talking 95% of the area, but I've already used 68%. So on your calculator, you're going to do 95 minus 68. I'm picking up 27% more, and I'm going to divide by 2. And I'm picking up 13.5%. And the last one, it's 100%. I've already got 95%. 100 minus 95 is 5. Split it in half, and each of these little areas is 2.5%. When it's an area, we're going to talk about it as a decimal. But for these problems, it a lot of times makes more sense to talk about it as a percentage. All right. Now, here's what I want to do. It says the following table presents a U.S. Census projection for the percentage of the population age 65 and over for each state and D.C. Use the empirical rule to describe the data. Now, this tells you to use empirical rule. It has to either tell you that or say that it's bell-shaped. So what we know is we know that this rule is going to hold, this 68, 95, 100. Okay, so 68%, 95%, 100%. All right, now what I'm going to give you on this, I'm going to tell you that mu is 13.249 from the calculator. And I'm going to tell you that the standard deviation sigma is 1.683. And what I want you to do is draw a curve like what I showed you on the other page. I'm going to put my mu in the middle, 13.249. And I'm going to go 1, 2, 3, 1, 2, 3. This time, though, I'm going to do 13.249 plus 1.683. You're going to add that in. All right, and then I'm going to add it again. All right, and going the other way, I'm going to do 13.249 minus 1.683. And then I'm going to do that 11.566 minus 1.683. And then I'm going to do this number minus 1.683 again. Now, once you get here, label your mu, makes it easier to see. Sketch in your curve. And if I go too fast, just cut off the video. All right, and once you've done that, remember on the other page how we talked about the percentages? If I go 1 standard deviation, I'm picking up 68% of the data. All right, so this would give me 34 and 34. And if I go 2 standard deviations, I'm picking up 95% of the data. On your calculator, do 95 minus 68 and split it. And the numbers are going to be the same every time. Once you know how to do it, you could just copy it off of something. And the last one is going to be 100. And all of these are approximately. And I do 100 minus 95 is 5, and I split it 2.5%, and 2.5%. Now, what it's going to ask you, it's going to ask you stuff like what percent of states are between 14.932 and 16.615 as far as the population of people over 65? And you're going to say 13.5. Or what proportion of states are between 8.2 and 18.298? And you're going to say almost all. I want you to look at this one. If you're looking at this line that goes through the mean, if you look at that, each side of the curve has an area of 50%, 0.50. And you'll be asked different questions like that where you need to tell what percentage is between, say I said what percentage is between 9.883 and 13.249. You would add this percentage and this percentage. All right. The empirical rule can be used for samples as well as populations. When we work with a sample, all you do is use X bar in place of mu and S in place of sigma. It does the same thing. I've got a class of 200 students taking an exam. The sample mean is 65 and the sample standard deviation is 10. It tells us the histogram is approximately bell-shaped. It's telling you that so you can use empirical rule. And then it's asking you how many students have scores between 45 and 85. All right, so I'm going to come down here and I'm going to make a curve. And my mean is 65. My mean is X bar this time, and my standard deviation is 10. Sketch in your curve. And sometimes it might be enough to just do the basics. And here's what I would call the basics. One standard deviation is 68%. Two standard deviations is 95%. And three standard deviations puts me at 100, approximately, for all of them. Now this, whoops, let me take that one out further. This question says approximately how many students had scores between 45 and 85. And if you look at 45 and 85, I can tell that this is 95% of my students, 95% of the people. So I want 95% of 200 students. Change 95 to a decimal, do 0.95 times 200, or you can do 95 over 100 times 200. Percent means per 100. I'm going to do 0.95 times 200. And I get about 190 students. Pause the video and I want you to tell me if in each case whether it would be appropriate to use the empirical rule. And I'm going to tell you it doesn't matter about mu and sigma, it matters about the shape. All right, this one would be yes, it's bell-shaped. Purple one would be yes, bell-shaped. Green one is no, it's skewed right. Red one is no, it's skewed left. So empirical rule holds for the two that are bell-shaped. Empirical rule does not hold for the other two. And that's what brings us to our last thing today. What can I do if I have something that looks like that or looks like that? What can I do? And that's what we are going to talk about next. And what that brings us to is something called Chebyshev's inequality. And when a distribution is bell-shaped, like what we just talked about, we're going to use the empirical rule. It is the best. You want to use that if you can to approximate the proportion of data within one or two standard deviations of the mean. Another rule called Chebyshev's inequality holds for any data set. So if you look back at these shapes that we've just talked about, Chebyshev's would work for all of these. Chebyshev's is not as precise as empirical, so I would not want to use Chebyshev's for the blue one or the purple one. I would use Chebyshev's if I cannot do empirical. And in order to do empirical, it has to say use empirical, or you have to look at it and realize it's bell-shaped. Now this is what Chebyshev says. In any data set, doesn't matter the shape, the proportion of the data that is within k standard deviations of the mean is at least 1 minus 1 over k squared. Specifically, if I set k equal to, I'm going to do 1 minus 1 over 2 squared. And I would type that on the calculator just like that. And what it's going to give you, it's 1 minus a fourth, it's 3/4, or 0.75. And what that's telling you is it's saying at least 75% of the data are within 2 standard deviations of the mean. And if you look at your formula, notice it did not start at 1, because if you put in 1 for k, you get 0, and that doesn't tell you anything. Now, if I put in 3, I'm going to do 1 minus 1 over 3 squared, which is 1 minus 1/9. You can type it just like that on the calculator, which is 8/9, which is 8 repeating, 0.8 repeating. And then here's what this is going to say. At least, most of the time it rounds us to 88.9. 88.9% of the data are within 3 standard deviations of the mean. Now, I want you to read this example, and once you've read it, I want you to note at the end that it tells you to use Chebby. It does not, even if it did not tell you to use Chebby, you would have to use Chebby because this problem does not say bell-shaped. All right, so what I'm going to do, it says the mean is 120. And the standard deviation is 10. I'm going to go 1, 2, 3, 1, 2, 3. Now notice I didn't leave a whole lot of space to draw a curve because I'm not going to draw one because I do not know the shape of this curve. It could be any kind of shape, so I'm not going to draw it. I'm going to take my standard deviation out. It's 120, 130, 140, 150, and then go the other way, 120, 110, 100, and 90. And this is what Cheby's tells you, okay? Cheby's tells you absolutely nothing about this. Okay, so Cheby's doesn't tell us anything about 1 standard deviation. If you go out 2, it tells you that you're picking up at least 75% of the data. And if you go out 3, you're picking up at least 88.9%. And that's what Chebby tells you. And then it would ask you questions like, Professor Short said that systolic blood pressures were between 100 and 140 for 50% of the population. Does this support that? No, because it says at least 75. All right, and things like that. Cheby's and empirical rule are good because they tell you about the proportion of data set within a given number of standard deviations. The plus about Cheby's is it applies to anything, but it's a rough approximation. Empirical rule is much better if you can use it.